Hello! So you've just learned all about the theory behind CycleGANs. And in this notebook, we're going to define and train a CycleGAN to read in an image from a set X and transform it so that it looks as if it belongs in set Y. Specifically, we'll look at a set of images of Yosemite National Park, taken either during the summer or the winter. The seasons are our two domains, X and Y. And here are some example images. In general, you can see that the summer images are brighter and with more green than the winter images. And the winter images contain things like snow, cloudy images, and brown or kind of dead foliage. The differences are not always so obvious though. Often rocks and water will look really similar no matter the season, so this is an interesting transformation task. Our main objective will be to train generators that learn to transform an image from summer into winter and vice versa. These images do not come with labels and are referred to as unpaired training data. But CycleGANs give us a way to learn the mapping between one image domain and another using an unsupervised approach. For example, in the paper that introduced CycleGANs, linked here, the authors were able to translate between images of horses and zebras, even though there were no images of a zebra in exactly the same position as a horse, or with exactly the same background, and so on. So a CycleGAN is made of two types of networks, discriminators and generators. The discriminators are responsible for classifying images as real or fake, for both summer and winter images in this case. And the generators are responsible for generating convincing fake images for both domains. So two domains, two types of discriminators and generators. This notebook will be mainly about defining and training these networks, but let's start by loading in our data to work with. I've provided some code in this notebook to load in our summer and winter image data and our usual resources. Then I'm creating training and test loaders for each of these image domains X and Y. This code should look pretty familiar, so I'm going to go over it pretty quickly. The getDataLoader function returns training and test data loaders that transform our image data into tensor image types. Then the data loaders can shuffle and batch this data into a specified size. You can leave all the parameters in this loader function as is. This will resize our images and create small batches. Alright, so I'll run this cell and then create loaders for our test and training X and Y data. Note that I'm defining our summer images as our X domain and winter as our Y domain, and this choice is just arbitrary. Alright, then I'm going to display some of these images. In this cell, I have a function that takes in a tensor image and converts it to a NumPy image for display. Then I'm getting some images from our X domain. Getting a batch of data from our data loader will naturally return a set of images and their labels. But the labels don't matter in this case, and actually they're meaningless here. Okay, so I'm displaying some of these summer images, and you can see that there's quite a variety of images. Some have people in them, some are quite hazy and may be mistaken for winter images even. Then I'll do the same thing, but for some of our winter images. And here again, you can see quite a variety of images. But in general, these winter images have a kind of different color palette. You'll end up seeing more whites and blues in these images than in our summer images. I've actually never been to Yosemite, but this is making me want to go. Okay, then the next step I'm doing is a pretty familiar pre-processing step, which is transforming these images from a pixel range of 0 to 1 to a range of -1 to 1. And I'm just printing out some of these values for my own sanity, so I can see that the image range originally is from about 0 to 1, and then after I scale it, it's from about -1 to 1. Recall that we typically use a tanh activation function that scales our generated images to a range of -1 to 1. So this step makes our training image data match the output of our generator. Okay, all of this code is given to you, and next you'll be able to access this notebook, and I'll describe the actual structure of the discriminators and generators for us to define.